Good day, juniors. Mr. Reynolds here to talk a little bit about intensity and polarization. We're going to split this lesson into two parts. The first, we're going to talk about what intensity is, look at some of the equations for intensity, and then second, we're going to take a look at polarization, which does a lot with intensity, so it seems like a natural thing to do. First, I want to show you a little image I put up on the screen. I thought it was pretty interesting. On the y-axis, we see the frequency of electromagnetic waves. Radio, microwave, infrared, visible light, ultraviolet, and X-rays and gamma rays. On the x-axis is sound frequency. Now you may notice these graphs are sort of weird. These are actually logarithmic graphs. If you graphed everywhere from 10 to the 9th to 10 to the 18th, then pretty much everything would be at the very bottom. Same thing with the x-axis. We use logarithmic graphs. But you'll notice here in this tiny little area right here, this is what we experience. This is what we see and hear. It's just a tiny, tiny fraction of all the different types of waves that are out here. In the bottom it says, in the grand scheme of things, we're pretty much all blind and deaf, which I think is sort of interesting. Of course, there are some other waves that we do sense. And those are infrared waves. Okay, infrared waves are going to have a lower frequency somewhere down here. So not totally complete, but pretty close. I thought that was pretty neat. But let's talk a bit about intensity. Intensity is the power per unit area. Let me explain what I mean by that. So imagine I have a light bulb, and that light bulb is giving off a certain amount of energy. And then I put a sheet of paper right next to the light bulb. Some of the light from that light bulb does indeed hit that sheet of paper. It's going to light up the sheet of paper, and that piece of paper is going to receive a certain amount of energy every single second. Remember, energy per time is what power is on a certain little area. Now, if I told you this light bulb was 60 watts, and let's say the piece of paper was 1 square meter. Right? Intensity is power per unit area. In other words, saying intensity is power over area. So the question would be, what would the intensity be on that piece of paper? Now, if you were a lesser student, maybe a biology or a chemistry student, you might think, well, that's easy. 60 watts of that light bulb is hitting that 1 square meter, so the intensity must be 60 watts per square meter, and that's unfortunately where you are incorrect. That's not right. Because here's the deal. That 60 watts from the light bulb, the 60 joules per second that light bulb is giving off, it's not being given off in only one direction. It's being given off, for the purposes of what we're dealing with, in all directions. And most of the energy that is given off by that light bulb doesn't come anywhere close to hitting that piece of paper. So the intensity of the light on this sheet of paper is much, much, much less than 60 watts per meter squared. Now, another way to think about this is, let's say I pull this piece of paper away. Let's say we move the piece of paper back. Is that sheet of paper going to be receiving the same number of waves or less waves from that light? If you move the paper back, more waves are going to miss the sheet of paper, and it's actually going to receive less photons, less light per unit area. So if I move that sheet of paper back, the intensity actually goes down. This is an idea we call the inverse square law. Let me show you a quick image we have here. I've got a little graphic set up for you here, because the internet can provide a graphic much better than I can draw it. So imagine here at the center we have a power. There's a source of power P. What happens is, let's just say in 1 second, that source of power, light bulb, the sun, whatever, produces this energy, sends it in all directions. Now, as time moves on, that surface of energy starts to spread out. It spreads out in a sphere. It spreads out in a sphere. All the energy that was let out in that tiny, tiny little amount of time is filling up a sphere. As the sphere gets bigger and bigger and bigger, as that wave travels away from the source, the concentration of the energy is going to get less because that sphere is going to get bigger and bigger and bigger. And so in order to find the intensity of a source, intensity is power over area, what we do is we actually use the surface area of a sphere, which is 4 pi r squared. R would be the distance to source. P over 4 pi r squared. And you can see here, if I double the distance between the source and my measurement spot, if you double that r value, your intensity will go down by a factor of 4, or be multiplied by 1 over 4, because it is squared in the denominator. This is why they call it the inverse square law. So at a position r, you see down here, we have intensity I. At 2r, we have I over 4. At 3r, we have I over 9, because look, that same energy that was filling up our little square down here at I, now has to fill up 4 squares, or 9 squares, or 16 squares, or so on. Now, in topic 4.3, they use a slightly different version of this equation. What they do is they say that intensity is proportional to x to the negative 2, where x in this case means the same thing as distance to the source. Now remember, that proportional symbol does not mean that intensity equals the inverse square of the distance, but it simply means if the inverse square of the distance doubles, so does the intensity. Remember how proportionality works. This means that I is equal to some constant value multiplied by x to the negative 2. In this case, the constant value would be p over 4 pi. So if you want to use the p over 4 pi r squared equation, go ahead. If you want to use this equation, you can as well. That will ask you probably a lot of questions like, hey, if you double the distance, what will happen to the intensity, and things like that. So this is how we deal with the inverse square law. We also, by the way, this is going to be very important next chapter. Next chapter is astrophysics. This is one of the ways that we can sort of figure out how bright stars are, because the light from stars works the same way. We will actually calculate the intensity of the sun at the surface of the Earth using information we know about the sun and the Earth and things like that, using this equation down here, I equals p over 4 pi r squared, and we'll find it pretty close. The only problem is next chapter, astrophysics calls intensity brightness, and they call power luminosity. But it's the same difference, and they'll call R D instead of X or R. So sometimes the variables do get a little mixed up, but this is how that works. There's the other equation we talked about the other day, looking at intensity and amplitude. Intensity is proportional to the square of the amplitude, which means if you have two identical waves of intensity I constructively interfere. If two waves are constructively interfering, their amplitudes are being added together. And so two identical amplitudes being added together, so that's 2a. 2a squared has the intensity of those two waves is 4 times I. We did this with double slit. We know the central maximum of double slit diffraction, since they are two waves, is 4 times the intensity. If it's 3 slit diffraction, then it's going to be 9 times the intensity. I is proportional to amplitude squared, just as I is proportional to the inverse square. So this is a little bit about intensity. Intensity, we often think of intensity sort of like power sometimes, but it goes a little further. Intensity is power per unit area. And remember what power is. Power is the amount of energy per unit time. So really you could think of it as energy over time times area, which we very rarely will do. So by the way, the unit for intensity you always will use is the watt per meter squared. It's the derived unit from all that. And the letter we use for intensity is always I. Okay. So this is a little bit about intensity. Now, how are we going to use intensity? Well, we're going to talk about intensity a lot next chapter, but for right now, we're going to talk about it in terms of a polarizer. Polarizers are one of my favorite wave property things. I know that sounds sort of silly to say, but you can do some really cool things with them. If I had some with me right now, I would be showing you in my camera. I'd be doing cool things. I don't have any in my house, so I know it seems weird, but I don't. So I'm going to link you a video where the guy's going to show you a few demonstrations of polarizers, and then I'm going to come up with another video here, and we're going to go through some of the equations they want us to be able to do with polarizers. So for now, Mr. Reynolds signing off. See you in just a moment.